Welcome to this problem walkthrough. In this session, we'll be tackling LeetCode problem number 1696, Jump Game 6. This problem challenges us to optimize a path with the highest score while adhering to specific constraints. It's a great exercise to sharpen your dynamic programming skills. Let's dive in. In this problem, you are given an integer array called nums and a number k. The array is zero-indexed, meaning that the first element is at index 0, the second at index 1, and so on. Your goal is to start at index 0 and reach the last index of the array, which is n1 if the array has a length n. You can jump from your current index I to any index j within the range I plus 1 to I plus k. However, each jump comes with a cost, and that cost is determined by the value at nums, j, the index you are landing on. The task is to maximize your total score, which starts with the value at nums, 0, and is updated as you make jumps. The output of the problem is the maximum score you can achieve when you successfully reach the last index. Let's look at an example. Suppose the input array is nums equals 1, minus 2, 4, minus 7, 3, and k equals 2. Here, you start at index 0 with an initial score of 1, which is nums, 0. From index 0, you can jump to indices 1 or 2, but a more optimal move is to jump directly to index 3, which is within the range of 1 to 2. Landing at index 3 yields an additional score of 4, so the total score becomes 1 plus 4 equals 5. From index 3, you can jump to indices 4 or 5, and the best choice is to jump to index 5, adding 3 to your score. This results in a total score of 5 plus 3 equals 7. Thus, the maximum score you can achieve for this input is 7. Another example uses nums equals 10, minus 5, minus 2, 4, 0, 3, and k equals 3. Starting at index 0 with a score of 10, jumping to index 3 and then to index 5 gives the maximum score of 17. Now, for a slightly more complex example, consider nums equals 1, minus 5, minus 20, 4, minus 1, 3, minus 6, minus 3, and k equals 2. Here, you begin at index 0 with a score of 1. From index 0, you can jump to indices 1 or 2. If you jump to index 2, which is within the range, you add nums, 2, equals dash 20 to your score, resulting in 1 to 20 equals dash 19. From index 2, you can jump to indices 3 or 4. If you choose index 4, you add nums, 4, equals dash 1 to your score, resulting in dash 19, 1 equals dash 20. Continuing this pattern, you can jump to index 6, adding nums, 6, equals dash 6 to your score, and so on. This example demonstrates that the problem does not always guarantee a positive score, but the goal is to still maximize it based on the given constraints. Finally, let's review the constraints and edge cases. The length of the array nums can be as large as 100,000, so the solution must be efficient and scalable. Each value in nums can range between dash 10,000 and 10,000, meaning that the array can contain both large positive and large negative numbers. The jump distance k can vary between 1 and n1. For edge cases, if nums contains only one element, the score is simply the value of that element, as no jumps are needed. If all elements in nums are negative, the solution must carefully navigate to minimize the negative impact on the score. Additionally, the implementation must handle large inputs within the constraints efficiently to avoid performance issues. These considerations ensure the solution is robust and handles all possible scenarios effectively. To solve the Jump Game 6 problem, we first consider the brute force approach. The intuition here is straightforward. From each index, we explore all possible jumps to subsequent indices within the range of k steps and calculate the maximum score recursively. For instance, starting at index 0, we evaluate jumps to indices 1 through k, and for each jump, determine the maximum score that can be achieved from that point to the end. The recursion terminates when we reach the last index, where the score is simply the value at that position. While this approach is conceptually simple, it's computationally expensive. The time complexity is O(n squared), because for each index, we iterate through a range of up to k indices, and the space complexity is O(n), due to the recursion stack or memoization table used to store intermediate results. However, this method has significant drawbacks. It performs redundant calculations for overlapping subproblems, making it inefficient for large inputs or scenarios with high values of k. To address the inefficiency of the brute force approach, we can optimize using the sliding window maximum technique with a DEEK. The idea is to utilize a dynamic programming array, DP, where DP, I, represents the maximum score to reach index I. Instead of explicitly evaluating all possible jumps within the range, ik, I1, we use a DEEK to maintain indices of DP values in decreasing order of their scores. This ensures that the front of the DEEK always holds the maximum score within the current sliding window. For each index I, we first remove indices from the DEEK that are outside the range, ik, I1, as they are no longer relevant. Then, the maximum score in the valid range can be found at the front of the DEEK, allowing us to calculate DP, I, as the sum of nums, I, and DP, DEEK, 0. To ensure the DEEK remains sorted in decreasing order, we pop indices from the back if their corresponding DP values are smaller than DP, I. Finally, we add the current index I to the DEEK. This approach is highly efficient, achieving a time complexity of O(n), since each index is pushed and popped from the DEEK at most once. The space complexity remains O(n) due to the storage of the DEEK and the DP array, making it a scalable and elegant solution. The chosen strategy for this problem is the sliding window maximum approach using a DEEK. This method is highly efficient, operating in linear time, which makes it particularly well suited for large inputs. The key insight lies in recognizing that the problem can be simplified to maintaining the maximum score within a sliding window of k elements, and a DEEK enables us to do this optimally. Compared to the brute force approach, which is easier to implement but computationally expensive, the DEEK-based solution offers significant performance advantages. It avoids redundant calculations and handles large values of k effectively. While the implementation is slightly more complex, the trade-off is worthwhile given the scalability and efficiency of the solution. Overall, this approach strikes an excellent balance between time complexity and space usage, making it the optimal choice for this problem. In this problem, we aim to find the maximum score achievable by moving through an array from the first index to the last. Each index in the array has a score value, and at any position, you can jump up to k steps forward. The challenge is to decide your jumps strategically to maximize the total score by the time you reach the last index. To solve this, we'll use a dynamic programming approach in combination with a sliding window technique. The idea is to maintain a rolling window of the maximum scores from the previous k indices, which allows us to make optimal decisions at each step without recalculating values repeatedly. By doing so, we ensure the solution remains efficient even for large arrays. Let's start by initializing a DP array, where DP, I, will represent the maximum score achievable to reach index I. Additionally, we use a DEEK, or double-ended queue, to store the indices of the most relevant elements for computing the maximum score in the current sliding window. This DEEK will help us maintain the maximum efficiently as we iterate through the array. We begin by setting up the base case. Since we start at the first index, the maximum score at index 0 is simply the value at nums 0. Thus, we initialize DP 0 equals nums 0. The DEEK is also initialized with the index 0, as it represents the starting point. From here, we loop through the array starting at index 1. At each step, we first remove indices from the front of the DEEK if they are no longer within the valid range of the sliding window, defined as the last k indices. This ensures the DEEK always represents the current window. The front of the DEEK now holds the index of the maximum DP value within this window, so we use it to calculate the score for the current index I as DP, I, equals nums, I, plus DP, DEEK, 0. After updating DP, I, we clean up the back of the DEEK by removing indices whose DP values are less than or equal to the current DP, I, as they are no longer useful for future calculations. Finally, we add the current index I to the DEEK, ensuring it's available for the next steps. Once we complete this process for the entire array, the last value in the DP array, DP, N1, will give us the maximum score achievable to reach the last index. The key to this algorithm's efficiency lies in the sliding window optimization. Instead of recalculating the maximum score for every window of size k, we use a DEEK to maintain and retrieve the maximum value in constant time. This DEEK is monotonic, meaning it's kept in decreasing order of DP values. By structuring it this way, the front of the DEEK always provides the maximum score for the current window. This ensures that we don't waste time comparing or recomputing values unnecessarily. The algorithm combines this DEEK-based optimization with dynamic programming, where the DP array stores the maximum scores at each index. Together, these structures allow the solution to run in linear time, as each index is added to and removed from the DEEK at most once. This efficiency, combined with the space savings from the sliding window approach, makes the algorithm both fast and memory efficient. To maintain the DEEK efficiently, we perform two key operations at each step. First, we remove indices that are outside the current sliding window range. This ensures that the DEEK only contains relevant indices for the current step. Second, we remove indices from the back of the DEEK if their DP values are less than or equal to the score at the current index, as they will no longer contribute to maximizing future scores. Once the DEEK is updated, we calculate DP, using the maximum value from the front of the DEEK, ensuring we are always making the optimal choice at each step. When considering edge cases, the algorithm handles them naturally. For example, if the array has only one element, the result is simply that element. If k is greater than or equal to the array size, the sliding window includes all indices, effectively summing the entire array. Additionally, the algorithm handles negative scores correctly, as it always selects the maximum achievable score at each step, even if that maximum is negative. This robustness ensures the algorithm works correctly across a wide range of inputs. Here, we start by importing the DEEK class from the collections module, which will help us efficiently manage the sliding window. Inside the maxResult method, we begin by initializing some variables. N stores the length of the input array nums, and DQ is our DEEK, which will be used to maintain the indices of the maximum scores within the sliding window. We also create a DP array of size n to store the maximum score we can achieve at each index, initializing DP 0 to nums 0, since the first position score is simply its own value. The first index, 0, is added to the DEEK. Now, we iterate over the rest of the indices in the array, starting from 1. For each index I, the first step is to ensure the DEEK only contains indices within the current sliding window of size k. This is done by removing indices from the front of the DEEK if they fall out of range, specifically if DQ 0, I, k. Next, we calculate the maximum score at the current index I. This is done by adding the value at nums I to the score stored at the front of the DEEK, which represents the best score achievable within the current window. After computing DP, we need to update the DEEK to maintain its properties. Any indices at the back of the DEEK that have a DP value less than or equal to the current DP, are removed. This ensures that the DEEK always contains indices corresponding to the highest scores in descending order, which allows us to efficiently retrieve the maximum score in constant time. Once the DEEK is updated, we append the current index I to it. At the end of the loop, the DP array will contain the maximum scores for all positions. Finally, we return DP-1, which represents the maximum score achievable to reach the last index of the array. Here, we start by importing the necessary Java utilities and defining our solution class with the method maxResult. This method takes in an integer array nums, representing the game board, and an integer k, which specifies the maximum jump length. The goal is to calculate the maximum score achievable by jumping through the array. We first initialize n as the length of nums, and create a DP array to store the maximum score achievable at each index. The first element in DP is set to nums 0, since that's where we start. Next, we declare a DEEK, which will help us efficiently track indices of maximum scores within a sliding window of size k. Initially, we add index 0 to the DEEK. Now, as we iterate through the array starting from index 1, we first remove indices from the front of the DEEK that fall out of the current sliding window. This ensures that the DEEK always contains valid indices within the range of the last k elements. The new score at DP, is then calculated as the sum of the maximum score from the DEEK's front and the current value nums, I. This step ensures that we are always building the maximum score achievable up to the current index. Finally, we remove indices from the back of the DEEK where the DP value is less than or equal to the current DP, maintaining the DEEK in descending order of scores. After updating the DEEK, we add the current index I to the back of the DEEK for future calculations. This ensures that the DEEK always tracks the indices that could potentially contribute to the maximum score for upcoming elements. Once the loop completes, the maximum score for reaching the last index of the array is stored in dp, n1. We simply return this value as the result. By combining dynamic programming with a DEEC for efficient sliding window management, this implementation achieves an optimal solution for the problem, with a time complexity of O(n). This compact and efficient approach allows us to handle large inputs while ensuring correctness. To solve this problem, we start by initializing the variables. The length of the input array nums is 6, so n equals 6. We also initialize a dynamic programming array dp of the same size, with dp, 0, set to nums, 0, which is 1, and the rest set to 0. Additionally, we create a DEEC DQ to help us efficiently manage the sliding window, starting with index 0. Now, in the first iteration for I equals 1, we check if there are any indices in DQ that fall outside the current window of size k equals 2, there are none to remove. We then calculate dp, 1, as the sum of dp, dq, 0, and nums, 1, which gives 1 plus, minus 1, equals 0. Since there are no elements in the DEEC with a dp value less than or equal to dp, 1, we simply add index 1 to the DEEC. Moving on to I equals 2, we again find no indices outside the window, so we calculate dp, 2, as dp, dq, 0, plus nums, 2, which equals 1 plus, minus 2, equals dash 1. Similarly, no DEEC elements need to be removed, and we add index 2 to the DEEC. At this point, the DEEC contains indices 0, 1, 2. Now for I equals 3, we first remove indices that are outside the current window of size k equals 2. Index 0 falls outside as k equals 1, so we remove it from the DEEC. We then calculate dp, 3, as dp, dq, 0, plus nums, 3, which results in 0 plus 4 equals 4. At this step, we remove indices from the back of the DEEC where dp, dq, dash 1, is less than or equal to dp, 3. This means indices 2 and 1 are removed since their dp values are less than 4. We then add index 3 to the DEEC, leaving us with dq equals 3. Next, for I equals 4, no indices fall outside the current window, so we calculate dp, 4, as dp, dq, 0, plus nums, 4, which gives 4 plus, minus 7, equals dash 3. Since no elements in the DEEC meet the condition for removal, we simply add index 4 to the DEEC, making it 3, 4. For I equals 5, we remove index 3 as it falls outside the window. We then compute dp, 5, as dp, dq, 0, plus nums, 5, resulting in dash 3 plus 3 equals 7. Finally, we remove index 4 from the DEEC since its dp value is less than or equal to dp, 5, and add index 5 to the DEEC. The final result for this example is dp, 5, equals 7. In this second example, the input array is nums equals 10, minus 5, minus 2, 4, 0, 3, and the window size k equals 3. We start by initializing dp with the first element of nums, so dp, 0, equals 10 and the rest are zeros. The DEEC DQ begins with index 0. For I equals 1, no indices fall outside the window, so we calculate dp, 1, as dp, dq, 0, plus nums, 1, which gives 10 plus, minus 5, equals 5. Since no elements in the DEEC have a dp value less than or equal to dp, 1, we add index 1 to the DEEC, resulting in dq equals 0, 1. For I equals 2, again no indices are outside the window, so we compute dp, 2, as dp, dq, 0, plus nums, 2, yielding 10 plus, minus 2, equals 8. Here, we remove index 1 from the DEEC because its dp value of 5 is less than dp, 2. After this, we add index 2 to the DEEC, leaving us with dq equals 0, 2. When I equals 3, there are still no indices outside the window, so we calculate dp, 3, as dp, dq, 0, plus nums, 3, which equals 10 plus 4 equals 14. At this point, we remove indices 2 and 0 from the DEEC because their dp values are less than or equal to dp, 3. We then add index 3 to the DEEC, resulting in dq equals 3. For I equals 4, no indices need to be removed from the DEEC due to the window size, so we compute dp, 4, as dp, dq, 0, plus nums, 4, which is 14 plus 0 equals 14. We remove index 3 from the DEEC as its dp value is less than or equal to dp, 4, and then add index 4, leaving dq equals 4. Finally, for I equals 5, no indices are outside the window, so we calculate dp, 5, as dp, dq, 0, plus nums, 5, giving 14 plus 3 equals 17. We remove index 4 from the DEEC and add index 5, resulting in DQ equals 5. The final result for this example is DP, 5, equals 17. In the third example, we have nums equals 1, 2, 3, 4, 5, and k equals 3. Since every number in the array is positive, the solution will maximize scores at every step. The DEEC efficiently maintains the largest scores for each window, ensuring that the highest possible value is used in each calculation. By the end of the process, the dynamic programming array DP accumulates the maximum scores, and the final output is DP-1 equals 15. In this solution, we're employing a dynamic programming approach with the help of a DEEC to efficiently manage the sliding window operations. Let's first focus on the time complexity step by step. For initialization, setting up the DEEC and allocating memory for the DP array is straightforward. Initializing the DEEC is a constant time operation, O(1), while creating the DP array takes O(n), where n is the length of the input array, nums. Next, the outer loop iterates through the indices of the nums array, starting from index 1 up to n1. Since this loop runs n1 times, the contribution to the overall time complexity is O(n). Now, within this loop, the operations on the DEEC play a critical role in maintaining efficiency. First, we have the removal of out-of-window indices, which ensures that indices outside the current sliding window of size k are discarded. This is done with the condition while DQ and DQ, 0, I, k. Each index is added to and removed from the DEEC at most once, so the total cost for these removals is O(n). Next, we ensure that the DEEC maintains a monotonic order of DP values. The condition while DQ and DQ-1 equals DP, I, removes indices from the back of the DEEC if their corresponding DP values are smaller or equal to the current value. Again, since each index is added and removed from the DEEC at most once, this operation also contributes O(n) in total. Finally, adding the current index to the DEEC is an O(1) operation performed once per iteration, which sums up to O(n). Combining the operations inside the loop with the loop itself, the overall time complexity is O(n). Turning to space complexity, the memory usage comes from two main components, the DP array and the DEEC. The DP array is used to store the maximum score for each index and requires O(n) space, as it needs to store one value for each of the n indices. The DEEC, on the other hand, holds indices for the current sliding window. Its size is limited to at most k, the sliding window size. In the worst-case scenario where k equals n, the DEEC could require O(n) space. Adding these together, the total space complexity is O(n), as the DP array dominates the memory usage, and the DEEC doesn't exceed this bound. To put this into perspective, let's compare the optimized approach with a brute force method. A naive solution would involve iterating through all possible jumps within the range, ik, I1, for each index. This requires nested loops, leading to a time complexity of O(n*k). In contrast, the optimized approach, which uses a monotonic DEEC, avoids redundant calculations and reduces the time complexity to O(n). The DEEC efficiently tracks the maximum score in the sliding window, ensuring that operations are performed only when necessary. This significant improvement makes the optimized approach far more suitable for larger inputs. Finally, let's analyze the best, worst, and average cases for the optimized solution. The best case occurs when the DP values are strictly increasing, meaning each addition to the DEEC results in no removals. Even in this scenario, the time complexity is O(n), as each element is processed once. In the worst case, where DP values are strictly decreasing, every addition to the DEEC leads to multiple removals. However, since each index is added and removed at most once, the total number of operations remains O(n). In the average case, the number of DEEC operations is proportional to the sliding window size, which is bounded by O(n). Mathematically, each index is processed in constant time during addition and removal, leading to a cumulative O(n) for all indices. Combining the space required for the DP array and the DEEC, the space complexity remains O(n). Both the time and space complexities are efficient, making this solution well-suited for large input sizes. One of the most common mistakes when solving problems like Jump Game 6 is overcomplicating the solution. Beginners often try to account for all possible edge cases right from the start, which can lead to convoluted code and unnecessary debugging. Instead, it's better to focus on implementing the core logic first and handle edge cases later. Another key pitfall is ignoring the constraints provided in the problem. Constraints like the size or range of the input are there to guide your approach. Failing to consider them can result in solutions that are inefficient and exceed time limits. For recursive implementations, not defining proper base cases can cause infinite loops, leading to Stack Overflow errors. Always ensure your recursion has clear termination conditions. Additionally, dynamic programming solutions often fail due to incorrect or incomplete state transition equations. It's crucial to carefully verify how the current state depends on previous ones. Lastly, neglecting to test edge cases like empty inputs, single-element arrays, or extreme values can lead to failed test cases during interviews or submissions. These edge cases are often where solutions break, so testing them thoroughly is a must. Now, when it comes to interviews, recognizing underlying patterns and problems can be a game changer. For example, problems involving recursion, sliding windows, or prefix sums often follow familiar templates. Spotting these patterns early can drastically cut down on problem-solving time. Additionally, understanding the trade-offs between space and time complexity is critical, especially for dynamic programming problems. For instance, you might use space optimization techniques like rolling arrays to reduce memory usage. This is a common follow-up question in interviews, so it's worth preparing for. Another important point is to always explain your thought process clearly. Even if your initial approach isn't optimal, walking through your reasoning shows interviewers that you have a structured methodology. Don't forget to explicitly address edge cases as part of your solution. Interviewers often probe these to assess your thoroughness. Also, practicing related problems can help solidify your understanding. For example, LeetCode 70, Climbing Stairs, introduces basic recursion and memoization. LeetCode 198, House Robber, is a great example of maximizing value under constraints. LeetCode 300, Longest Increasing Subsequence, focuses on subsequences, and LeetCode 746, Min-Cost Climbing Stairs, involves minimizing a cost function. Each of these problems builds skills relevant to Jump Game 6. Finally, it's important to be aware of alternative approaches and their trade-offs. A brute force approach evaluates all possible solutions and is often the simplest to implement. However, it's rarely practical for large inputs due to its poor time complexity. Still, brute force can be useful for validating results on smaller test cases. Recursive solutions with memoization are another option. They avoid redundant computations and are easier to write for some problems, but they come with higher space complexity due to the recursion stack. Bottom-up dynamic programming, on the other hand, builds the solution iteratively and is generally more space-efficient since it avoids recursion. However, it requires careful initialization of base cases to work correctly. Lastly, in certain variations of problems, greedy algorithms may offer faster solutions with lower time complexity. However, greedy approaches can fail when the problem requires global optimization, as they focus only on local decisions. Each method has its strengths and weaknesses, so choosing the right one depends on the specific problem and its constraints. Great job! In this problem, we explored a dynamic programming solution enhanced with a DEEC for range optimization. This approach helped us achieve an efficient solution for Jump Game 6. Remember to practice similar problems to solidify the concepts. Thanks for joining, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!